in here we're just going to skim right through because we don't necessarily need it. So to get those verifiable results, the metric system is used, and in particular we have what's called the MKS system: meters, kilograms, and seconds. So this is what you'll need to write down. Measurements always involve units. So our base unit for length is always going to be the meter, and we abbreviate that with an M. Okay. The base unit of time is always going to be seconds, and mass is always going to be kilograms. So that's where we get MKS. So in physics, we use the MKS system. Okay. So all of our lengths are always measured in meters. All of our masses are always measured in kilograms, and all of our seconds are always measured. Time is measured in seconds. Okay. So, for example, well, no, I don't mean. Now, the next thing we're going to talk about is if everybody's got to do the same thing and going to use the same unit, we have to make sure that those units actually mean something concrete. Feet, where did the unit of feet come from? Does anybody know? Anybody know? Feet was a unit of measure for length, but it was based on the king's foot. So a foot was the size of the king's foot. Is that concrete? Like going to stay the same all the time no matter what? No, because you could have a really tall king who's got really big feet, or you could have a really short king who has really tiny feet. So the length can change, which is not very helpful when we're doing scientific experiments. We need something that's this length no matter what forever. So most of the time we think of a meter, we think, oh, well, it's a meter stick. Well, who made a meter stick that length? What makes a meter stick that length? So we're going to look at the standards that we use to make a meter, that what says a meter is actually a meter. If that makes sense. So, long time ago, we started coming up with these standards. And they've changed over time. Don't need that. Here we go. So for a meter, the standard of length for a meter is the distance traveled by light in a vacuum. In 1,299,792,456 part of a second. Whew, that's a lot to say. Now, you don't have to memorize that. It's not, I'm just telling you where it is. It's not like I'm going to test you, and if you get one digit wrong, then I don't know, you're wrong. No. Just want you to know that that's where that meter stick comes from, that length. It's the distance that light travels in that teeny tiny fraction of a second. That's not going to change. Okay, that's going to stay, it's constant. And that's what we need. We need our units to be backed up by something that is constant. Okay. So that comes out to approximately 3.28 feet. And speaking of lengths of things, our towers, Peyton and Marco, y'all were second place. Kevin and Adam, first place. Braden and Landon and Luke, if your little tassely thing had stood up straight, you would have won. But it flopped over, and I couldn't get it to stand up straight. So, yeah. Okay. All right. So there's some typical distances. Again, you don't have to write that down. That's in your book. All right. So masses. Mass is a little bit different. Mass is still the only thing whose standard is an actual physical object. Because physical objects can change, like the king's foot, we tend to not like to use those as our standards, but mass is the only one that is still a physical object. So it is a platinum iridium cylinder, and it is protected in the Bureau of Weights and Measures in France. And it is kept in a very, very, very protected environment so that it doesn't change. Okay, so it's got 2 cylinders so that not even a speck of dust gets on it and changes the mass of it. So until we can find something that we can measure mass with that's not a physical object. So just know that 1 kilogram is an actual little cylinder. Right. Okay. The next one is time. And again, this table is in your book, so we're not going to go over that. Yeah, we do need to talk about this before we talk about time. So, the difference between weight and mass. Now, we throw those 2 words around as if they were the same thing, but they are not the same thing. Hopefully, remember that from physical science and stuff. Mass is an intrinsic quality, meaning it is unchanging. Intrinsic properties are properties that do not change regardless. Weight, on the other hand, is a measure of gravitational force. So it changes depending on your location. Okay? Mass is the same always, no matter where you are, whether you're here on Earth, whether you're on the top of Mount Everest, whether you're on the moon. Your mass will be the same. Okay? But your weight will change depending on those locations. So you can take your weight here and it'll be one thing. You can go on the top of Mount Everest and it's going to be different. You can go to the moon and it'll be different still. You can go to Saturn and it'll be different there too. Okay? So because it just depends on the force of gravity, and the force of gravity can change depending on your location. Okay? If you're on the moon, your force of gravity is 1/6 what it is here on Earth. If you're on a planet like Saturn, it's going to be greater than what it is here on Earth. Okay, so it's just a matter of where you are. So please make sure that we understand that those 2 things can be very, very different. And when I say, so please do not say weight when you mean mass, because if you do, I will have to count that wrong. Okay? So don't use those interchangeably. All right, talking about time. Time is based on an atomic clock. Okay? So specifically, here's the standard measurement of time. It is, so 1 second is defined as the time it takes for the radiation from a cesium-133 to oscillate 9 billion and something times. So a cesium atom, the time it takes for it to vibrate 9 billion times, that's a second. That's pretty much what that means, okay? Oh, yeah. Speaking of time. We got that. That's a big number, so I'll leave that there for a second. 9,192,631,770 times. There we go. Okay. All right. And supposedly that is better than our old means of measuring time, because in old means, depending on the rotation of the Earth is not always exactly the same. It may slow down at some points, it speeds up at some points. So a clock can be off, okay? But cesium atom is going to vibrate all the time. And it's going to vibrate, for the most part, it's going to vibrate at the same speed all the time. So the time that it takes for that many vibrations is 1 second. All right. Prefixes. So we kind of know that already. So I'm just going to go to this screen and we're going to tell you the ones that you have to have memorized. Okay. And then that's going to lead us into good old dimensional analysis. Y'all remember that? Yay! Changing from one unit to another. You're going to be doing so many dimensional analysis conversions in this class. Okay. So you need to have memorized from mega all the way down to micro. Okay, so you need to know that mega is 1,000,000. So it's 1,000,000 times bigger. Kilo is 1,000, which you should remember that one from elementary. Hecto is 100. Deca is 10. So that's why we like the metric system. It's all prefixes of 10. It's all measures of 10. So 10 to the 6th, okay, that's 1,000,000. 10 to the 3rd, 3 zeros, that's kilo. 10 to the 2nd, that's hecto. We got 2 zeros. You see the relationship between the exponent and the zeros. Okay. We got 6 zeros, we got exponent of 6. We got 3 zeros, 10 to the 3rd. We got 100, we got 2 zeros, that's 10 to the 2nd. 1 0, 10 would be 10 to the 1st power, that's deca. And then once we get past deca, we start going in the other direction. So deca, hecta, kilo, mega, those are all bigger than the base unit of meters or grams or seconds, okay? But when we get to deci, we start going, they're smaller. So deci is 1/10. So we say that's 10 to the -1. It's smaller than a meter, okay? Centi is 1/100th, and milli is 1/1000th, and micro is 1/1,000,000th. Okay, so 10 to the -6. The negative means it's a fraction, it's in the numerator, or I'm sorry, denominator, and then the 6 means there's 6 zeros. Okay. All right, all the equations that we're going to use, and this will be on the next slide, and I'll underline it in just a second. But all equations in physics have to be dimensionally consistent. That means that it has to be length, or you have to make everything work out and cancel out to get the same unit on both sides of the equation. Okay. So that's why you're going to have to make sure you use your dimensional analysis so that you get those units to cancel out. Okay. So everybody got this down?
What is the micro symbol?
It is, okay. That's a good question. The micro symbol is a Greek letter M. So it's kind of like you do a swoop and then you make an M. Yeah, it's a Greek letter. Sorry, it's the one I always forget because it's the only one that's a Greek letter on here. So micro is this weird looking M with a tail. Milli is just a plain old M. Centi is a C. Deci is D. Deca, which by the way we never use deca. You very rarely do you see those as a unit. Is DA. Hecto is H. Kilo is K. And mega is a capital M. Okay. Hecta and deca we do not use very much. They're just not normally used. The ones you'll see the most are mega, kilo, milli, centi, and micro. You might see nano a couple of times, but I'm not making you memorize that because you'll probably be able to look that up. Okay. All right. Okay. So, dimensions and units. We need to know the difference between a dimension and a unit. All right. So, dimension is a physical quantity that refers to the type of quantity it is. So, a dimension can be length or mass or time. Those are dimensions. Okay. Your unit is going to be kilograms or centigrams or decigrams. But your dimension is the gram. It's mass. Okay. So if we look at these two as an example, both of these are distances, 25 kilometers, 1.25 centimeters. The dimension for both of those is the same, and that they are both measures of length, but the unit is different. One's a kilometer, one's a centimeter. Okay, so you need to know the difference, because I may, when I'm correcting a paper or something, I might say your dimension was wrong. You need to understand that you put length and it should have been time or something like that. But if I say your unit is wrong, that means, okay, my dimension is right, it's length, it's just the wrong length. I forgot to convert my units. Okay, so in equations, you have to have all the same dimension. Okay, so just writing that down, and we'll look at an example of what we mean. Physics the math is not terribly hard because it's just going to be solving an equation. The hard part is going to be figure out which equation do I need to use for which problem, because you're going to have a ton of them to choose from. So you've got to learn how do I choose which equation is going to fit my problem. And actually, even that, once you get the hang of it, is not that hard. Okay, you're going to pick the equation that has all the variables that your problem has, right? So if you're looking at force and mass and acceleration in your problem, you're not going to pick a formula for velocity, because that doesn't have force in it, and it doesn't have acceleration in it, and it doesn't have mass in it. So you got to learn to look at your problem and look at what's in it, and then you find your equation that goes with it. Then you make sure all of your units cancel out correctly. And then that's really all there is to it. So when we get to vectors, it gets a little more complicated with vectors. That's where we have to throw in our sine and cosine and tangent. And other than that, it's not that much different. Okay, so let's clear this, and let's go to the next screen. All right, so there's some examples of dimensions. The ones we've talked about are real easy because they're just mass and grams, mass and length and time. Those are easy. Ones that get a little bit different from what you're used to is ones like velocity, where we're going to take a length and divide it by a time, and we come up with a new unit. We call it a derived unit because we derived it. We made it. We took one thing and we divided by another, and there's our unit. Okay. Acceleration is another example of that. You have length, you divide it by time squared. Okay, so again, this is in your textbook. It's a table in your textbook, so you don't necessarily have to write it down, and we'll be writing it down a lot in the coming days. So, all right, this is something I do want you to write down, because this is what we mean by having our problems be dimensionally consistent. Okay, so here's what I want you to write down. Let's say we have this as our equation. Okay, lots of algebra in here, so lots of letters, and then we replace them with numbers. So x final equals xi plus vt. That just means your final distance, where you end up, is equal to where you started plus how fast you were going and how long you were going. That fast. Okay, that's all that means. I'm not worried about that part right now. What I do want you to notice is that when we put the units in here, final distance is length, initial distance is length, velocity is length divided by time, and time, of course, is time. So when we do all of that math, time cancels out, and all we're left with is length. That's how we know this is correct. I used the right formula. I got the right answer because my units, my dimensions are consistent. Time canceled out, left me with length all the way across. Okay? If this hadn't canceled out, you'd be like, oh, okay, something's wrong. I'm not using the right, something ain't right here. Which is why in this class, you cannot just put in numbers. You have to put in the number and the unit that goes with it. Because you have to make sure your units are going to cancel out and it's going to be dimensionally consistent. That's just a way to check yourself and make sure that you got your answer right before you have me say, no, that's wrong. Okay? It's just a way to double check yourself. So always make sure that your units will cancel out correctly and you have the same unit on both sides of your equal sign. Okay? Does that make sense? Okay. Does everybody have that written down? And perfect timing. We're left off. We'll do dimensional analysis tomorrow. Yay! Something to look forward to. Your safety test is your only homework for tonight. Okay? So just have that safety test done tonight. And then Friday or Monday, we'll start doing problems. All right? Good, bad, ugly so far? How was it? Very good? Huh? Right now, it's simple stuff. So just keep remembering, we're starting with the simple stuff, and we're just going to add little bits. Just a little bit more every time. It's like when you weight train. You just add a little more weight every time. That's what we're doing. All right, y'all have a good day. See you tomorrow.
Where are you going there, Phil?
Yes, ma'am.
Do you, can I just hand these to you?
Oh, yes. Thank you.
I
Yes,
can
yes,
wait
yes.
if it's
No.
easier.
No. This is perfect.
And
I actually forgot to ask more.
The adult form, I wasn't sure what to do. I think it's this one. It didn't have a react signature, so I just signed it. It said adult, and I was like, oh shoot, but I've already done it because it said I am the person. Anyway, so
Yeah,
if
I
I need to
know.
redo that, I
Actually,
can.
yeah,
But
if you could just cross your name out and have your parents,
Okay.
one of your parents sign it.
yes,
Yeah, that's fine.
Here is a schedule request form. It just says to turn it into a classroom teacher. You can't take it to the office.
Oh, okay. All right.
I don't know what you're supposed to do.
Okay. Thank you.
Oh,
Okay.
I'm
And you, all right. Thank you very much. Or Jacob. All right. You gotta go all the way down that hallway, make the curve, and you'll just keep going straight, and you'll run straight into it. I believe her door, when you're in the hallway, there'll be two doors. Her door is this one on the left side. Keep walking till you run into the door.